everybody. Can you hear me? Welcome to today's colloquium. Today I have the privilege of introducing an old friend and a remarkable scientist, Matthias Rempel, who is some of you will know. Matthias is a staff scientist at the High Altitude Observatory. And well, I have a lot of bio data here about him. But I think if there was such a thing as a Man of the Year award in solar physics, Person of the Year award, probably today this person will be Matthias, as he has produced the most realistic, detailed and credible numerical simulations that exist of sunspots and active regions. Some of you have been involved in conferences and meetings lately and seen how rare it is to find a session in a conference where this work is not mentioned at some point or another. And I think it's interesting that it's very timely. This work, by the way, I think was just published in Science just a few months ago. Yeah. It's very interesting that this work is very timely because, as you probably all know, we are living a very anomalous time of solar activity. We're living in a solar minimum life that we have seen in 100 years. So there are really any real spots to look at. What we really want to look at are these simulations to study and analyze. So anyway, just some bio data about Matthias. He got his PhD in 2001 from the University of Göttingen. Although he had actually been research mostly at the Case Institute and the Max one. And then, since 2002, he has been working in Europe, first as a postdoc, and then in 2004, he became a conversation there. So, we're very fortunate that we have very remarkable, and it's great to have you to talk about.
Okay, thanks for the kind introduction, and also would like to start thanking the ISC for this invitation, giving me the opportunity to present this work, but also talk to people who are actually pioneers in the observational study of sunspots and the sunspot fine structure. Now, this talk is today mainly about theory, mainly about simulation, so since there's limited time, I won't talk too much about the observational side, but I hope we can discuss this intensively after this talk. Why do we study sunspots? There are many aspects, and I just have here basically three main points. Sunspots are the most prominent manifestation of strong magnetic field in the solar photosphere, which is related to the solar cycle. In that way, they are the key for understanding the inner workings of the sun, the solar dynamo. In order to understand this further, we have to study the origin of sunspots, flux emergence process, the subsurface structure. And this, of course, also ties into the solar-stellar connection to star spots and the operation of stellar dynamos. And understanding stellar magnetism is still one of the big open questions in stellar astrophysics. If we turn more to the sun, sunspots obviously the key for understanding the magnetism in the outer layers of the sun from the photosphere upward. I won't touch too much on this one. And this talk will be mainly here about the last point, which is really their excellent plasma lab for studying the interaction of magnetic field and convection in detail. And that really means looking at the sunspot fine structure with all the aspects, umbral dots, penumbra filaments, evershed effect, mode flow, and the detailed magnetic structure. So if we focus more now on this aspect, I mean, the kind of details I want to address in this talk are basically here the details related to the energy transport in sunspots, umbral dots, the penumbral filaments, which are here seen in very high resolution by the impressive work of Görer and Charmer. It shows nicely, I mean, some umbral dots here not clearly visible, but clearly the filament with the substructure with dark cores in the center. The evershed flow, which was exactly discovered 100 years ago, and we are still trying to figure out exactly how it is driven, a flow along these filaments away from the sunspot with a velocity of several kilometers per second. Then on a slightly larger scale, you also have light bridges in sunspots, which show some similarity also to these filaments, and I will show later some simulations where you also get some light bridges. On a little bit larger scale, sunspots also influence the environment and change the large-scale flow pattern around them, which leads to mode flows. So far, we have not seen too many of the mode flows in this simulation, but I will show one simulation where there's some evidence for them too. And of course, we want to understand also the subsurface structure of sunspots. Are they just a monolithic block of magnetic field? Is it more fragmented beneath the surface? And this also ties into then the connection to helioseismology, since there are in principle methods also to probe the subsurface structure through looking at the sound waves in the sun. Now, on the theoretical side, there have been many different modeling approaches, and there have been, for more than 30 years, idealized MHD simulations, which typically just use the ideal gas law and no radiative transfer, which pointed out already some aspects which are most probably related to fine structure in sunspots, and these are studies of 2D and 3D oscillatory magnetoconvection in vertical and inclined fields, some 2D axisymmetric sunspot models. There were models of Rohr convection, and all these models, they give some insight, but it's in general very difficult to compare them to observations, since they simply don't have had very often the 3D structure and also didn't have radiative transfer, which really allows to make a very close connection. Then there's another class of models, more simplified and partially motivated by observations, and I guess in the last 10, 15 years, most of the discussion was here around the either flux tube models or gap models. In flux tube models, energy is transported primarily through flows along flux tube. The gap model, which was more recently proposed by Sprout and Charmer, convection happens in almost field-free gaps in the sunspot penumbra. These models, they have the advantage that they can match some observational constraints pretty well, but they are strongly limited due to strong assumptions which are made. They're not really models from first principles. And then there are realistic MHD equations, simulations, which really include the realistic equation in state and the sufficiently sophisticated radiative transfer. But they are very expensive, and this is actually a story which began as far as it concerns really simulated sunspots and parts of sunspots. It started only very recently, about 4 years ago. But before I go there, I just want to summarize some of the difficulties one encounters if one tries to simulate the sunspot. The first problem is sunspots are on a very large scale, 10, 20 megameters, so you need very often numerical domain, which is something like close to 50 megameters wide. At the same time, they have fine structure to the smallest scales we can observe today, which tells you that you most probably need a grid resolution, certainly much smaller than 100 kilometers. So you have to do simulations with very large grid sizes, so they are very expensive to begin with. Another problem is if you look at the characteristic velocities you will encounter, and here I just show the typical range of velocities if you look into a domain which is about 8 megameters deep. Most of the simulations we are doing have trouble with this mouse here a little bit. Yeah. Yeah. Okay, so we have a wide range of characteristic velocities, and maybe I'll just do this one if it works. So if you look at convective velocities, it's about 5 kilometers per second near the photosphere, 500 meters per second at the base of the convection zone. Sound speed ranges from 10 to 30 kilometers per second, but the biggest troublemaker is the Alfvén velocity above the umbra of a sunspot, where you can reach velocities in excess of 1,000 kilometers per second. If you have an explicit code, that will limit your time step, and basically it makes the simulation of this kind almost impossible. So what we do in this code is we have to do an artificial limitation of these high Alfvén velocities, which saves you about a factor of 100 in computing power. So it pretty much makes a difference between being able to do a simulation like this and not being able to do it. The reason why you can do something like this is the fact that the plasma beta is really extremely low here, less than 10 to the minus 4, down to 10 to the minus 6. So even if you limit the Lorentz force by a factor of more than 1,000, the Lorentz force still remains the dominant force, which means that the magnetic field has to remain very close to a force-free state. So you don't really change the topology of the field, but you slow down Alfvén wave substantially. Then the code we are using is a modified version of the Muram code, which was previously developed mainly by Alexander Völkler at the Max Planck Institute. And this code includes multi-ray radiative transfer using short characteristics in 24 directions. It has an option for non-gray radiative transfer, but for the simulations I present here, we did everything in the gray approximation. And it uses the Opel equation of state. One other difficulty is that you have a very inhomogeneous domain. You have a lot of different regimes. With high and low plasma beta, you have supersonic shock waves in some regions, and you have very quiet regions. The only way you can tackle that is really using a very robust numerical scheme with very highly nonlinear artificial diffusivity. It's also something not everybody likes to use, but this problem is really so diverse that you don't really get along doing something like that. So I told you already that the progress only using this type of simulation started maybe about 4 years ago, and the first simulation in this respect was the simulation by Schüssler and Völkler, focusing on umbral dots, which they basically focus on a very small region in the center of the umbra of a spot. So you could basically, it's basically like having a small box somewhere here in the center of this simulation, and they saw that umbral dots are basically almost field-free plumes which originate, they start originally like oscillatory convection, but the oscillatory convection transitions into overturning convection, creates almost field-free plumes. Then just a few years later, Heinemann, Nordlund, Sharma, and Sprout presented the first simulation which included the transition from an umbra to a penumbra using the slab geometry. So they basically simulate a narrow slab through the center of a sunspot that helps to save some computing power. And when I got into this business only a few years ago, we first started also with a slab simulation, but we increased the box size a little bit, going here to about a horizontal extent of 32, 36 megameters. In the vertical direction, we still have a very narrow slab of only 4 megameters, but I stacked here 3 on top of each other to make this movie. And you can basically see most of the elements of penumbral fine structure here. You have umbral dots and the transition to more elongated filaments and the transition from umbra to granulation. These filaments, they show dark lanes, they have a bright head. Some of them propagate inward during their formation phase. So these simulations could already show that there is a common magnetoconvective origin of both the umbral dots but also the penumbral filaments in the sunspot penumbra. And the key element in this process is overturning convection. And what happens in these, this shows cross-sections perpendicular to the filament, or if it's an umbral dot, it just shows a cross-section somewhere through the center of an umbral dot. Typically, you have an upflow in the center of the umbral dot or the filament, a downflow at the edge. And the upflowing plasma expands very strongly since you have a very strong stratification. As part of this expansion process, you overall weaken the magnetic field substantially, and you basically create a region which has a reduced field strength. And if you weaken the magnetic field sufficiently, at some point the magnetic field becomes sufficiently weak that you actually can have overturning convection. And this overturning convection leads to additional flux expulsion, which makes this gap almost field-free. If you have a penumbra and you start initially with an inclined field, this effect of the overturning convection on the horizontal and vertical field components is different. The weakening of the vertical field is much stronger than the weakening of the horizontal field. In this case, the gap doesn't become completely field-free, and instead you get an increase of the inclination angle, and the magnetic field inside these filaments is strongly increased, and this shows the inclination angle. When you have the strongly inclined field, you get as a side effect also horizontal flows along the filaments, which are shown here. And it was already recognized and mentioned in these lab simulations suggested by Sharma that most probably this effect is related to the formation of the Evershed flow. The problem with these early simulations was that this flow was very intermittent. You had it along these filaments in the center. Sometimes you see some evidence here that at the edges of the filament you also had opposite flows. So it was not very clear if this really can lead to a very coherent, almost space-filling Evershed flow, also with the amplitude of several kilometers per second. And we then went a big step further. Here I show roughly in the right relation the simulations I showed on the previous slides. And we went to a rather big simulation where we actually simulate an entire active region of two opposite polarity spots. And here, for the first time, we really see now a very extended outer penumbra, primarily in between the two spots, where, of course, because of the opposite polarity, you have more horizontal field. And you can here also see nicely that here the left spot has many more umbral dots than the right spot, and this is because we initialize this run such that the left spot has a weaker field, around 3 kilogauss, whereas the right spot has about 4 kilogauss field strength. So you might ask the question, why do we simulate two spots and don't just focus on one? The reason is, by combining them, you can address a lot of different questions in one simulation you would otherwise have to address by doing a series of simulations. All these simulations, they have some arbitrary initial state, so you have to do a series of simulations to see how sensitive they are. And you can do two simulations of individual spots, or if your code scales way to larger processor counts, you can just do one big simulation where you put both spots in the same box. And that actually allows you to evaluate a lot of combinations of different parameters. So we can have the spots at different field strengths, and then owing to the periodic boundary conditions, we basically have opposite polarity spots here in the x direction, while we have same polarity spots in the y direction. And so you have for each spot a wide variation, a combination of different inclination angles if you go around them, and field strengths. In that way, it actually allows you to evaluate many more combinations as you could do if you would do separate simulations. And we did the simulation using a grid resolution of 32 kilometers in the horizontal and 16 in the vertical direction, which for the box size we consider here, which is about 100 times 50 megameters and about 6 megameters deep, leads to about 1.8 billion grid points. And here I show a magnetogram movie which shows the vertical field at the tau equal 1 level, and the bottom shows vertical cut through the center of the two sunspots displaying the field strength. And if you look at this magnetogram movie, you can see already, if you look here at the region where you have the penumbra, you see strong evidence of flows diverging from the sunspots. There's a lot of magnetic flux advected away from the sunspots. You can also see, due to the setup, we have, of course, the two penumbras of the two spots coming very close, and the two Evershed flows, they have to collide and they form a big downflow lane here. You can actually see this in the evolution of the subsurface field. You see a lot of magnetic field drag down. And you can also see clearly in this magnetogram movie the evidence of the fine structure, which shows up here as these very narrow gray filaments, which basically show there is zero field strength in most of these elements, the umbral dots and the penumbral filaments. Now, if you look at some large-scale average quantities, I look here at the narrow slice through the center of the two spots, and shown here are averages along the y direction, and then it's additional average for about 1 hour in time. The top panel shows the magnetic field strength in red, about 3 kilogauss for the left, 4 for the right spot. Blue is the horizontal field, and green is the intensity, normalized here to the quiet sun intensity. And the intensity in the umbra of the two spots is about 15–20%. In this penumbra region in between, it's about 80% of the solar luminosity. But we have also, the penumbra starts already a little bit further in. We have variations in intensity somewhere between 50–80% in the penumbra of these sunspots. The bottom panel shows the relation between the average inclination angle of the magnetic field and the presence of large-scale horizontal flows. The blue curve here shows the inclination angle, and these vertical dotted lines mark the regions where the inclination angle increases 45 degrees. And whenever the inclination angle increases 45 degrees, we get a horizontal outflow from the spot, which increases with the distance from the spot and reaches mean values of up to 6 kilometers per second in the penumbra, which is here in between the two spots. Peak values of this flow can be somewhere in the range of 13 to 14 kilometers per second. And I also want to point out that, as I explained before, we have here a variety of different combinations of field strength and inclination angles. So we actually have 4 quite different penumbra regions. But this rule that the evershed flow begins when the inclination angle exceeds 45 degrees seems to be rather robust with respect to that. This is now a movie which shows a vertical scan through the magnetic field structure of the right sunspot in the simulation. On the left side, I show the vertical field component. On the right side, the radial field. The value of the magnetic field here shows basically where I cut off the field strength in this plot, and this is the depth level with respect to the photosphere and the quiet sun. You see very near to the bottom of the box, you have a lot of these interchange instabilities where field-free plasma penetrates from outside into the sunspot. And very likely, if you would run the simulation for much longer, at some point they would show up as light bridges in the visible layers of the simulation. Then, if we wait for it to come back up again, and maybe I should stop the movie at some point. So now we come back up again from below, and here you don't really see a lot of fine structure in the field strength, but if you approach the tau equal 1 level, suddenly, roughly the uppermost 500 kilometers of the simulation, you suddenly see all these almost field-free regions in the vertical field showing up, which are related to umbral dots and penumbral filaments. And then if you go above the tau equal 1 level, of course, the magnetic field becomes very smooth again, since it has to be since it is in a low beta region. And this fine structure shows up primarily in the vertical field. There is some evidence also here in the horizontal field component, but it's much weaker. If you look at the flow field, this is again a scan through the domain. Here I show the vertical velocity, blue is up, red is down. At each height level, it's normalized by the RMS velocity. And this is the radial velocity, where red means flows away from the sunspot. And what you can see is, you see this ring of outflowing plasma pretty much at all height levels. In the outer regions, it's always more space filling. It's more intermittent in the inner part, but it's present at all height levels. If you look at the convective pattern, you actually see evidence of convection cells also at all height levels. The size of convection cells in this penumbral region is comparable to the size of convection cells in the granulation outside. If you approach the upper layers very close, to the surface, these convection sails become more elongated and more anisotropic. No. This plot now shows axisymmetric averages of the radial outflow from the sunspot. Color-coded is here the depth level. Red colors are very close to the photosphere, so if we average over the entire spot, the velocity which remains is about 3 kilometers here. And near the bottom is blue. The velocity is much smaller here. It's still an outflow, but you also have to take into consideration that in this domain, the density is almost changing by 3 orders of magnitude. So even though the flow velocity down here is much less, actually most of the mass flux is in the deeper layers. And here I show vertical profiles of the evershed flow at different locations in radius. Red is more at the inner edge and blue more at the outer edge. You see the flow peaks very close to the tau equal 1 level here, which is at z equals 0, and then declines inward. And this decline is very similar to the typical depth variation you see for convective flows, which is primarily 1 over pressure scale height factor. You also see some evidence that the flows change sign above the tau equal 1 level and they change to inflows. But we have to be a little bit careful in these simulations since our equation of state and a lot of other things, the radiative transfer, are not that well if you really go far above the tau equal 1 level. So just to summarize very briefly these large-scale properties, in this simulation we have a pair of sunspots with 3 and 4 kilogauss field strengths. We get dark umbras with about 20 or 15% of the mean intensity of the quiet sun. Umbra dots are primarily present in the weaker spot. We have a Wilson depression. I didn't show it, but it's somewhere around 600 kilometers after we ran this for about 4 hours. And we have intensities in the penumbra somewhere in the range between 50 and 80%. And the presence of horizontal flows is very strongly tied to the inclination angle of the magnetic field. And the critical angle turns out to be in the simulation 45 degrees, but we have quite a variety of different penumbra regions here. And it seems to be a rather robust result. We can get average flows up to 6 kilometers per second if you look at the penumbra in between the two sunspots, but peak flows can be much larger. We have a weak indication that these evershed flows actually it's stronger in these stronger spots, the spot on the right, which overall looks more coherent. And these outflows are not just a surface effect, they're present at all depth levels. They show a decline in amplitude, but since the mass increases much quicker with depth, most of the mass flux is actually in the subsurface layers. I would like to focus now a little bit more on the detailed structure of the penumbra. And in this movie, I show now here a magnetogram. This panel shows the inclination angle of the magnetic field, where dark red is vertical and bright yellow is horizontal. And here in the bottom, I show the radial flow velocity and again the vertical flow velocity. And you see in this plot very nicely this structure of the penumbra, which shows a lot of variation in the inclination angle. You have this narrow filaments with almost horizontal field embedded in the background, which has a much steeper field, which looks like the observationally inferred uncombed penumbra structure. And this inclination, this increase of inclination is primarily due to the fact that you see a strong decline in the vertical field strength in these filamentary structures. If you go further away from the sunspot center, you see also evidence of opposite polarity flux, which is primarily in the end of these convection cells where you have stronger downflows, which drag some of the magnetic field down. If you look at the flow structure, you see that these big patches of horizontal field, they coincide with the regions where you have the strong outflows. And you can also see that the scale of the vertical flow field is smaller than the scale of the horizontal flow field. Inside these outflow patches, you very often see several up and down flow cells. And here I want to show a few still images to show more clearly the relation between dark lanes, vertical flows, and outflows. So this is a part of the penumbra which shows here in the inner part some filaments which have a bright head and also dark lanes, which don't come out that way here on the screen. And if I blink this image now with the vertical flow velocity, you clearly see that all these bright heads corresponds to upflows. The region where you have the dark lanes is also related to an upflow. This is the filaments we also had before in the SLAT simulation, where you have a central upflow, and at the edges you have a downflow. And if I blink this again, you see clearly this strong relation between the flows. If you go into the outer penumbra, this changes a little bit. In the outer penumbra, you have more what is typically happening in normal granulation, and that means most of the bright features correspond to an upflow. If you look at this, for example, and what looks dark actually is a downflow lane. So you have two types of different dark lanes. You have the dark lanes of these filaments really in the innermost penumbra, where the dark lane is clearly associated with an upflow, which is an effect of this rather narrow confinement of these filaments. But if you go to the outer penumbra, it looks more like normal granulation. If I now go further and blink these two pictures which show the vertical and the radial flow field, you see in the inner penumbra again, that is the wrong direction. If you look again into the inner penumbra here, you see this relation that you have an outflow just along the axis of the filament where you have the upflow. But if you go into the outer penumbra, you have these very broad patches of outflow, but you have several up and down flows inside each of these patches. And this structure also becomes evident if you compute something like the correlation coefficient between vertical and horizontal flows. In the umbra and the inner penumbra, you have a correlation which is somewhere here about 0.6, which is positive, meaning that upflows are typically outward, downflows are inward. But somewhere in the middle of the penumbra, which is somewhere around here, a radius of 15 megameters, this correlation drops to 0 and it becomes weakly negative further out. That it's weaker in the outer penumbra is due to the fact that the outflow regions have both upflows and downflows, but there is a weak preference of downflows actually in the outer penumbra. As one would expect, the flow has to go somewhere. And here I also would like to compare the penumbra to granulation by looking at a few quantities like the RMS velocity and the typical scale at which mass is transported. And in order to compare this, I cut out of this box two regions which have roughly the same size. One region is here in the center part, cutting out the central penumbra between the two spots. And for the other region, I use the corner of the domain. And since the box is periodic, this is actually also just one box. These are not four little boxes, and they have exactly the same size. And here I show the RMS velocities. The black line is the total RMS velocity, and then I show here the different components. And if you look into the granulation, you see that the vertical RMS velocity is typically about 70% of the total, and the two horizontal velocities are here about the 50% level. That means about 50% of the kinetic energy is in the vertical motion, the other half is in the horizontal one. If you go to the penumbra, the overall RMS velocity is not substantially changed. It's a little bit higher, and it might have a little bit steeper increase towards the uppermost levels. But there is not much more kinetic energy in the flow. It's just in a different way distributed among the different components. The flow along the filament is obviously, that is here the red component is dominating. Now coming to the scales of mass transport, I guess there are several ways you can measure it. And we tried here a way by looking, basically comparing. So first of all, yes, if you take the total of the mass, vertical mass flux, it should be 0 since it's balanced. But if you take, if you take the total of the absolute value, that gives you a measure of how much mass is turning around at a given level. And in order to find a scale at which most of this mass is turning around, we do the following. We take the mass flux and we smooth it out over a certain scale. We take then the absolute value of this and integrate it over a horizontal plane in this box and compare that to just the total of the absolute mass flux. And if you increase the smoothing length we use in this approach, which is here the scale L, then what is left over in the mass flux should decline. If you don't smooth it at all, this is obviously 1. If the smoothing length is comparable to the size of the entire box, what is left should be 0. So how quickly these quantities decrease when you increase the smoothing length tell you roughly what is the scale over which most of the mass flux is turning over. And since we deal here in the penumbra, obviously with an anisotropic situation, we do the smoothing independently in the x and the y direction. So if we first look at the granulation, this is how these curves typically look like, and the color code is here shows these curves for different depth levels. Blue is the photosphere and red is somewhere 4.5 megameters deep. If you go into the photosphere and you increase your smoothing length to something like 400 kilometers, you roughly lose half of the mass flux. So most of the mass flux is turning over on scales on granules or a little bit smaller than that. If you do the same near the bottom of the box, the scale increases because the pressure scale height is larger and the overall size of convection is larger. Now if you use the same method and apply it to the penumbra, and here we did the smoothing in the x direction, which is along the filament, you see an increase of the scale in the photosphere, here to something from 400 to something like 1,000, 2,000 kilometers. But near the bottom of the box, the scale stays the same. If you do the smoothing in the y direction, which is perpendicular to the filament, the scales on average are reduced to smaller scales, which you expect since these filaments are, of course, more narrow in that direction. If you compute the geometric average, what you see is overall, the scales are not really fundamentally different. You just see a slightly enhancement from contribution at the very large scale, which is, of course, evidence you have something like large-scale flow, like the Evershed flow. But the enhancement is rather moderate. It's somewhere in the 10 to 20% level. And if you do a similar analysis to the energy flux, you see something similar, that most of the energy is transported on scales which are comparable to granulation. And the large scale provides only something like 10 to 20% of the total energy flux. So overall, this points to a convective structure of the outer penumbra, with the scale of energy mass transport are not significantly different from granulation. The same is true for the RMS velocity. The main difference is the anisotropy, which leads to an enhancement of flows parallel to the magnetic field without really changing the kinetic energy substantially. And the ordered horizontal flow leads basically to the impression of a large-scale flow, which is new compared to granulation, but it's really more a rearrangement of the horizontal flows you have in granulation anyway. The kinetic energy doesn't really change a lot. So in that way, one could say that the outer penumbra is a case of highly anisotropic granulation. And as I mentioned before, the contribution really from the large-scale flow is small, somewhere in the 10 to 20% range, primarily in the deep layers. In the surface layers, you don't see a very strong contribution. And if you look back into earlier work which has been done 20 or 30 years ago, you can actually, it's sometimes very interesting to see, to look back what people concluded when they had much easier simulations. They actually, if you read their conclusions, they were not fundamentally different. But what is, of course, different here now is that by having the third dimension added to the problem and also having radiative transfer, you can also show that these type of convection processes lead to a structure which can explain most of the elements of fine structure we can observe, and they can explain it based on a unified picture. You don't really have to reinvent the wheel for umbral dots, for penumbral filament, for light bridges, and all the different aspects. And relating this to some of these earlier work on magnetoconvection, one also should point out that the process which is behind this goes beyond oscillatory convection, which was typically considered there. since you see a transition from this oscillatory convection mode where plasma is just moving up and down on field lines to overturning convection mode, since the upward moving plasma can weaken the field to a degree that the overturning motion can happen. So overall, we see a unified picture for explaining the fine structure of sunspots. And the main ingredient which changes between umbral dots and filaments is inclination angle. If the field is vertical, you have these intermittent field-free upflow plumes, and they open inside a strong monolithic field. You don't require any subsurface structure which has already gaps in there. This magnetoconvection is powerful enough, even if you have a completely monolithic block of field initially, to create this fine structure. And these umbral dots, they have also a substructure. Very often they show dark lanes, which are Y-shaped, and this also has been recently found in observations. I think Thomas Rempel, he published a paper where they could see these dark lanes also in umbral dots. If you have a moderate inclination angle up to 45 degrees, you get these peripheral umbral dots and intermittent filaments in the inner penumbra, where you typically have a bright head, and then you have a tail which shows a dark lane. And the increased inclination angle which is present is also a consequence of the overturning convection, since it affects the vertical field component stronger than the horizontal one. And that there are horizontal outflows along these filaments in the inner penumbra is more a secondary effect. Most of the effects which create the horizontal field are related to the overturning convective motions. And this looks very similar to the observationally inferred uncombed structure of the penumbra. Then if you increase the inclination angle even more, you switch to the outer penumbra, where you have more these extended patches of horizontal field and flows, which is best characterized just as anisotropic convection. The organized flows are consequence of the anisotropy. And these horizontal flows are not just the surface effects, they are deep-reaching. You see the outflows at all depth levels. The scales of energy and mass transport are comparable to granulation. And if you look at the field geometry, I just traced here a few field lines through some of these filaments to show the transition from the inner to the outer penumbra. I highlight here two filaments. The red one is a typical filament in the inner penumbra, where you just see a small dip really in the field structure at the tau equal 1 level, but the field continues up to the top boundary of our domain. If you go to the outer penumbra, the horizontal flows finally become strong enough to completely overrun the field, and the field remains horizontal inside these filaments. And the key to point out here is really overturning convective motions are the central element of all of this. And I think future high-resolution observations really should target on trying to characterize this component of the flow field, which is currently only marginally accessible. Of course, these simulations are not perfect. I think we capture the essence of magnetoconvection energy transport, but they're still far from truly realistic, and how far they are is just if you really compare how a nice real sunspot looks like and how close we get right now with the simulations. You see most of the elements are there, but the filaments are not as densely packed. But you also see in the simulations is that the threshold for producing a penumbra seems to be very high. It's not that easy. It's not straightforward that you just put in a sunspot in these boxes and they always have a nice penumbra. If you start from a monolithic field, at least they like to stay like this. And I think the main shortcomings, and especially this one, might be related to the limited resolution and also the initial state we choose. Most probably, if I want to get it fully consistent, we have to simulate the flux emergence process in total, which is, of course, a completely much more complicated problem. And there's also some influence from the bottom boundary condition. And there are possible improvements we can do in the near future. If we want to beef up resolution, we have to go to nested grids. It's right now impossible to do a simulation on the scale and increase the resolution much further, since the computing power scales with the force power of the grid resolution. Going to deeper domains, but also focusing on the simulation of the flux emergence process. And I want to just very briefly mention some of the most recent work we are doing in that direction. But first, I want to tell you some aspects of the bottom boundary we were using so far in these simulations. These boxes are rather shallow. They're 6 megameters deep. And what we have to do is we basically have to fix the field at the bottom boundary. Otherwise, the sunspot would fall apart very quickly. Because over this rather short distance, the magnetic tension force is strong enough that anything which happens at the bottom boundary is immediately transmitted to the surface layers. So if some motions want to tear apart the sunspots down there, the entire sunspot would fall apart. Just to illustrate this, I show here 2 runs of a rather small sunspot or big pore with different boundary conditions. The first one is just what happens if you would have an inflow from beneath. You see it weakens the field to the degree that the umbral dots just can grow to granules, and once that happens, it takes apart the entire sunspot. The second boundary condition, it doesn't allow for a vertical flow, but it allows for horizontal flows and for exchange instabilities. And then you get something which looks already a little bit more realistic, that the sunspot just slowly deforms and some flux gets basically torn apart and transported away by granulation. This looks already much more like sunspots decay on the sun, but the problem is right now, this happens on a rather short time scale here of just something like 6 hours, which is essentially the overturning time scale at the bottom of this box. So the question is, what happens if you actually go to a much bigger and deeper box? And this is a simulation which is still running. This is the first sunspot simulation we did, now going to a box which is 16 megameters deep. And I show here the surface intensity image and the field strength at 1.5 megameters, 3.4, and about 11.5 megameters depth. And this covers about 23 hours. And what you can see is that, of course, in the deep layers, the large-scale convection pattern significantly deforms the sunspot. The field gets basically pushed into a downflow vertex of this granulation, but some of the flux gets basically also pushed into the downflow lanes of these big convection cells down here. And the flux, which basically gets dragged into the downflow lanes, that is basically leading to the separation of flux in the near surface layers, which you at some later stage can also see here then as shows up in the near surface layers as a light bridge. So, and what we see here is not totally unrealistic. I mean, sunspots, they change their shape, but the most important thing is that going to a deeper box, the situation doesn't become worse, it actually becomes better. We know, even though we have here, we relax the bottom boundary constraint a lot, the sunspot can survive 24 hours, and most probably it can be even still there if I run it for 48 hours, which I certainly will do. It's just, so far I only have 24 hours. And some of these events are even related to formation of light bridges, which is also happening in real sunspots. Other interesting thing you're seeing, there are a lot of pore-like features which just formed from some of the flux which got eroded from the sunspot. And if you look at those pores which survive a longer time, they are also related to flux which actually goes deeper down. The longer a structure lives on the surface, the deeper down it goes. And I also should mention that, of course, this simulation was done at a much lower resolution so that we can cover 24 hours or even more. So it doesn't really show a nice penumbra. The resolution is here 96 kilometers in the horizontal dimensions. Another way to go is trying to simulate the emergence of an entire active region. This is work which was primarily done by Mark Chung. And this is a small active region. The flux which finally ends up in the spots you will see pretty soon is something like 3 times 10 to the 21 Maxwell. So, and the field we used was strongly twisted, so you see a lot of rotation in these sunspots. And if you want to know more details about this, Mark Chung will be here, I guess, in 1 or 2 weeks when there's a flux emergence workshop. So he's the person to really ask about what's happening here. But essentially what we did is we used a box which is 8 megameters deep, and we initiated the flux emergence process by having a half torus moving across the bottom boundary as boundary condition. And then when the torus was moved in halfway, we basically stop this process and we just let the convection do whatever it wants to do with it. And you see it essentially runs through all the phases of the flux emergence process where you initially see strongly dispersed field and later it reassembles itself and forms more coherent spots out of it. So what is the future where we can go with these simulations? It's certainly higher resolution, deeper domains, flux emergence, in the hope that we will get bigger and bigger computers. I think the biggest challenge is going really to higher resolution, since as I said before, computing power required goes with the forced power of the resolution. And we are right, and this actually becomes a very tricky problem. Right now, we have a resolution where you can just resolve these filaments, but what this just resolving means that is any flow which is in there is a laminar flow because of numerical diffusion which is in the code. If we increase the resolution, we get the transition from a laminar flow to a turbulent flow in these filaments. As long as you're in this transition regime, you don't necessarily get very well converged results. So you might have to increase the resolution to a degree that you actually can get a resolved turbulent flow. If this means that you have to go a factor of 10, that means a factor of 10,000 computing time. That will happen at some point, but not in the near future. Most probably the only way we can achieve something like this in the near future, we really have to go to nested or adaptive grid so that you can do the big domain in order to get the overall field geometry very close to what the sunspot is, and then you just pick out a very small section of the penumbra with a nested grid where you can really refine on it. But even that will be still very expensive. What is more feasible in the near future is certainly going to the deeper domains, and what we so far can see in these deep domains is that certainly the dependence on the bottom boundary decreases, and the decay timescales for sunspots certainly go beyond a day. So it becomes close to what we would expect, and I guess if you go even deeper, it would become even longer. As part of this decay process, we can also get light bridges, and we also see some evidence for mode flows. I don't know if you saw it when I showed the movie, but if you look especially in this figure or in this one, and you look at some of these feed elements, you get the impression that they're actually diverging from the sunspot. This is a flow which is diverging from the sunspot with a few hundred meters per second. Some other thing I haven't talked about, but we are working on, is the helioseismic connection. Since these are fully compressible simulations, they include P modes, and this is a power spectrum of one of the 8 megameter deep boxes. The dark lanes here indicate where these ridges should be from a good solar model, and this is where the power is in the box, so it's right on, of course, except for the long wavelengths which feel the bottom boundary. And we can use the simulation as a forward modeling tool for wave propagation to sunspots, and of course use them to test and improve helioseismic inversion methods. You can just take an artificial Doppler-gram and try to invert it and see what you get out of it. And simulating this formation of sunspots is certainly one of the next big steps. Currently, we can do something on a scale of big pores. If you really want to go to an active region, we most probably have to go to a box of 200 times 100, something like 25 megameters deep. It would be already feasible today, but it's expensive. It's depending on how much resolution you want to throw it. It's somewhere in the 10 to 100 million CPU hour range. Okay, that is what I wanted to talk about today, so many thanks for listening.
Entirely satisfied with the penumbra in your sunspot? I mean, you still.
I mean, the question is, it comes down to, I mean, how far do you really need to drive the simulation? Do we need a simulation which really agrees with the sun to the last digit, or are we happy when we have a simulation which basically shows the essential elements of fine structure? I mean, that is a very general question. How far do we really need to go with this? If you really want to get the last things right, it will become exponentially more expensive. Yeah. Yes. That can well be, and right now, at the time we published the paper, we had about 3.6 hours, and whenever there's computing time available, I have it running in the background. Now it's somewhere at 4.2 hours, and I continue it. Most probably next Christmas time, when most people are on vacation, the computers are empty, I can do a few more hours on it, so we certainly look into it whenever we have the time to do it. Yeah. I mean, question is if you have good enough statistics to really make this claim. I mean, you can try to look at the long-term average maybe of the intensity. It might be, that might be something it's more reasonable to do most probably with a simulation like this one, which ran already 24 hours. And then really try to do a long-term average of the intensity to see if you see any evidence in that. I haven't looked into it, but yeah, azimuthal average and time average.
More questions? In my opinion, the simulation you show on the emergence of flux is a bit unrealistic in the sense that, at least for the large sunspots, you observe that they are made like fragments, and it's like a rope, emerging rope, where the fragments fit and merge, and then it is also related with the decay. They start to break in the more or less in the same stitches that the fragments were stuck. So, do you include that idea in your simulations, the possibility that the fragments are already compact?
I mean, we don't really have too much handle on details like this. I mean, we really, we don't really have a parameter we can change to make this happen except for the initial state. And of course, to keep it simple, we so far started always from initial states, which are rather monolithic, coherent fields. But of course, you would expect if flux is emerging from the base of the convection zone, by the time it reaches a depth of just 8 megameters, it's already very much fragmented. But of course, it's completely unfeasible to do right now. So you have to impose something at the boundary which is most probably unrealistic. So one of the next big steps with flux immersion simulations is, since we just don't know this bottom boundary very well, we have to do a parameter study, try different things, also different twist angles of these flux tubes to get a rough handle on how sensitive results are with that respect. Yeah. Maybe one could try something. I mean,
because the simulation you showed, I mean, the magnetic field is completely fragmented, and then the convection movement fuse them together or something, make them to merge into the sunspot. And that maybe is possible for small sunspots, but for the big ones, they are already formed. And the fragments are very big when they come up.
Yeah, I mean, this was also a rather small sunspot. I mean, what ended up, it's 3 times 10 to the 21 Maxwell, and just with the domain size we have, we cannot put in more flux than that. Actually, in this domain, the flux, if I remember the number correctly, the flux emergence process actually exchanged 40% of the entire mass in the box. So we drive already, in this case, a lot of mass through the box.
Okay, in relation with what Hector was saying about the simulations and if it can be more realistic, I think your penumbras are too short. I mean, I would say factor 2 at least. They have to be bigger. So for me, it's not just a detail. I think there is some fundamental ingredient missing because they have to. I mean, it's a great work. I'm overwhelmed with everything you've shown. It's excellent stuff, right? But the penumbras are too short, and I think there is something that is missing that doesn't make the penumbras as long as we observe them. So I think that's a critical issue that is not just running and running, because even in this simulation, it ran for quite some time, and the penumbra didn't have a tendency to become bigger and bigger. I mean, it stays the same, and they are sort of too short. So that's one question, and I have another question, which is more about the large-scale flow that you have there. I don't understand if you get something like a magnetoconvective flow. You know what I mean? Sunspots are supposed to have some cell. Some people put it in one direction, other people put it in a different direction, surrounding sunspot, and they call this the MOAT flow. And the MOAT flow is supposed to be leading to the sunspot extraction, generating muy magnetic features. These opposite polarity features that you see, I think, are more this overturning convection, as you said. So do you get any larger scale flow? I don't understand the larger scale flow in your simulations. You mentioned that, but
mean large scale flow beyond, I mean, the Evershed flow is also a large scale flow, right. But you mean larger than that scale.
Right.
I mean,
so, but the Evershed flow gets horizontal. Are you feeding the Evershed flow from below with mass somehow? I
mean, in principle, the domain has an open boundary, so flows don't have to close inside the domain. They can also
the bottom domain is open boundary.
Yes.
Okay.
So they can also close outside the domain.
Right.
So regarding mode flows, I mean, the high resolution simulation we can only right now, we have it only for 4 hours. That is not really enough to get something on a scale of a mode flow, which does, since it is a much larger scale, it needs more time to develop. The first indications for flows like this I see in this deep run, which I actually ran for about 24 hours now, and it will continue it. And there you see primarily this large-scale flows in the upper half of the box, and you see a weak inflow further down.
But these flows are being fed from below somehow.
Actually, most of this flow which is in this box, as far as I see it so far, they mostly close inside the box. Most of the outflow is in the upper half of the box. And, I mean, I haven't had a chance to look too much into detail in it, but the way it roughly looks like is that these flows are primarily present in the part of the domain in which the typical size of convection cells is smaller or equal to the diameter of the sunspot. Once you go so deep that convection cells are larger than the diameter of the sunspot, they just don't care if there's a sunspot or not, and so they have no reason to create any sort of large-scale flow.
So, according to what you are saying, and I finish with this, the Evershed flow is a larger scale flow, and you are also linking it to the MOAT flow. For you, Evershed flow and MOAT flow are linked with this larger scale flow. Traditionally, they have been completely separated.
I mean, not entirely, because...
Well, I think they are the same, actually. This is what we are publishing.
I mean, they might have a common physical region, but if they're really the same flow system, it's not clear, because particularly in this run, you have a flow diverging from the spot a little bit further away, but if you get more close to the spot, you actually have a flow converging towards the spot. So in this simulation, you certainly get something like a mode flow in the total absence of an Evershed flow.
Oh, you don't have Evershed flow there.
This one, since it has a very low resolution, you don't really get a nice penumbra, and this is an example where you can have a mode flow without an Evershed flow. But nevertheless, there might be a connection there that they have some similar physical origin, just on different scales. But you can have, at least as far as it looks like now, and I have to run it longer to get better averaging of all this, because you have a lot of noise, since you have, if you go to the deeper part of the box, you only have a few convection cells in there. But as far as it looks like in this particular run, you might be able to have a mode flow in the absence of an Evershed flow.
And just, you know, these short penumbra, why they are not 2 times larger?
I mean, as I said before, we see that it's very hard to get a penumbra at all in these simulations, and my strongest suspicion it might be related to the initial state. I mean, What we do in the simulation, we put in a monolithic axisymmetric field, which is basically the anti-penumbra state. So the convection really has a hard piece of work to carve a penumbra out of this. The flux emergence process puts something up there which is much more fragmented in the beginning. It can well be that there is some hysteresis in the problem which makes a difference. It's just very difficult to initialize this really with something completely different without really going through all the stages of the flux emergence process.
Any more questions?
You make synthesis of the source profiles, these simulations, and then rate the synthesis profiles to know the space resolution. Do you find a limit?
I know that Juanma Borrero, he's doing it right now, and he has some initial results, but I think he would really be the person to ask how close it gets. I mean, he sent me some results, but since I'm not too familiar with the Stokes analysis, I might be not the most qualified person to really comment on them. Yeah.
Yes, these simulations were done with reduced Lorentz factor.
We're done with...
reduced Lorentz.
Yes.
And so if you were to include the full Lorentz force, how much longer would the calculation have to be?
Factor of 100.
100. Okay, so that's impossible at present.
Yeah, the big spot simulation I showed here would be 100 million CPU hours if you want to do it the brute force way.
So another question is,
yeah.
I think at that point you should already begin to see if there is any color trying to hold the sunspot together. I mean, I'm referring back to these kind of ideas people had.
Yeah, I mean, what you certainly see is that the sunspot is, I mean, it ends up, most of the flux ends up in a vertice of these 3 big convection cells down here, or 4 convection cells. So if you compute the average convective flow of these cells, it's on average flowing towards the sunspot. So in some way it is like some of these flow fields proposed which keep it together. The only way the magnetic flux can leak out is by just going along the downflow lanes of these big cells. And that is related then to all these shape change you see in the near surface layers.
Okay, so in some sense the convective flows that develop.
It looks like this, but I mean, originally also, I mean, the first run I did, I still had, at the 60 megameter depth, I still fixed it at the bottom boundary because I was first very pessimistic and thought this will fall apart anyway, so start with the most restrictive boundary. But when I saw that it looks like it might actually stay together, I have now a second run running where I relax the boundary to allow also horizontal flows in the strong field region. But that is still not advanced to this point, but so far it looks like it doesn't really look much worse. But
the plasma beats there already quite high.
it's, I mean, I don't know exactly what the number is, but I had 16 kilogauss at 16 megameters depth. So I guess it must be somewhere close to 10 to the 3, I would assume. Yeah.
Any more questions? Well, thank you for an excellent presentation. I can we thank the speaker one more time?